All right. So, can you see the screen? Is it
Yes, I
visible
can
for
see.
everyone?
I can see the screen.
All right. Okay. All right. So let's start. Uh, we're discussing temperature and how we calibrate our thermometer. And thermometer is a device to measure temperature. We're specifically talking about the mercury in glass thermometer, which is nothing but a glass tube which contains mercury, and the temperature is measured in accordance with the physical quantity, that was the length of the mercury, which expands or contracts upon different being exposed to different temperatures, right? So that's something that we figured out, and we were doing trying to understand how can we calculate our temperatures using this property of mercury, right? It's a expansion and contraction property. It changes in its volume, or we can say changes in the length of this mercury thread. And so we have, this was the equation which helps us to determine the temperature of any material or substance that we use this mercury thermometer to measure. Right. So we saw that uh, we choose any appropriate substance, which is known as thermometric substance, and that was mercury in this case for a liquid mercury in glass thermometer. We saw that we'll choose two fixed points, and those two fixed points were the ice point and the steam point. We saw how do we measure these two fixed points by choosing two degrees of the standard degrees of how hot something. We use the example of water, how hot water is and how cold water is, and according to that we defined these two fixed points, and we recorded their values uh, and we marked them on the thermometer. That's how we set it up the scale, by dividing then the thermometer into 100 equal parts, because the maximum temperature was 100 and minimum is 0. So that's something that we did so far. And now coming back to the calculation of the temperature using this thermometer, if I think I'll go to the next page. Now we can do this. So for example, I wrote down this expression. I'll write it down over here again. The theta, which is the temperature, right? The temperature that I want is equal to L, length of the mercury tube at this temperature, minus length of the tube when it was at 0 degrees, divided by length of the tube when it's at steam point, which is 100 degrees, minus length at 0 into 100. And this is for degrees Celsius. So this is into 100 degrees Celsius. So now this will give you the temperature in degrees Celsius. Now these values L0 and L100 would be standard fixed values, right? So for example, I'm going to do, I'll just write it that these would be some fixed values according to those fixed points that we determine, right? And now let's try to figure out how we do this calculation by an example, right? So let's do a problem. The problem is that you have an unmarked mercury thermometer. So we just have this thermometer. If I draw it, I'll just do it very quickly. So this is my thermometer and it's unmarked right now, right? And the length of the mercury thread, when the temperature is 0, this standard length is given as 5 centimeters, right? And the length of this mercury in this tube, so this would be the mercury, right? And when it's at 100 degrees, the length of the tube is given as 25 centimeters. So these values are given to you. You want to figure out the temperature of a substance. So for example, you're trying to figure out the temperature of any substance, and you put this thermometer in that substance. It turns out that this length of the mercury is 14 centimeters. 14 centimeters. Can you tell me which variable is this? What variable is this telling me? Is 14
The
centimeters.
length of the temperature.
Right. So L theta, right? So this is the length of the mercury tube at the temperature that I want to determine. So I have put this tube inside in that material. So suppose this is that material, and the length of the tube becomes steady at 14 centimeters. So I'll write it down as 14 centimeters. Now it's very simple to do our calculation, because if you just remember this expression, then you just put these values in. So the temperature that I want to determine, theta, is equal to L
44,
at theta. We
45,
saw it's
45.
14 centimeters, right? Uh, L at theta.
Yes,
Why would
14.
it be 45?
It's the temperature I calculated already.
Okay. So, oh, so you're telling me the answer, right? Okay.
Yes,
So L at theta is 14 centimeters minus L zero. So when the temperature is zero, it's 5 centimeters divided by, at 100, we can see it's 25 centimeters. So 25 minus at zero, it's again 5. So this would be multiplied by 100 degrees Celsius, and this would become uh,
45 degrees Celsius.
45, 45 degrees Celsius. All right. So, okay. Can you still hear me, by the way? Just confirming. Yeah.
Yes, I can hear you.
Okay. Okay. So this would be 45 degrees Celsius, which means that the temperature of this substance is 45 degrees centigrade, uh, in accordance or in reference to these fixed values, right? So from the thermometer, we were able to determine the length of the mercury thread, from which we were able to use this expression, this formula, to determine this temperature. All right, so that's how we can use this liquid in glass thermometer to measure temperature. Now I'll just quickly talk about some of the common terms that we use with thermometers. There are very few we'll talk about. We'll talk about the first one, that is sensitivity of a thermometer. So how sensitive my thermometer is to the changes in temperature, right? So what does that mean? That means that if there are very minute, small amount of changes in temperature, how will the change in the length of the mercury behave, right? Will it be able to change its length with small changes in temperature? So the higher the sensitivity, the better the thermometer, because it will be able to measure even smaller changes in the temperature. Because if there are those changes in temperature, how will we measure them? By the changes in the length of the mercury thread, right? So if the length of the mercury thread is prone to those, I mean, the length of the mercury thread changes with those slight changes in temperature, then the thermometer's sensitivity is relatively higher. So we can say that sensitivity is the change in length, right, per change in temperature. All right. So how can I increase this sensitivity?
Uh, by changing the glass where the mercury is in.
Right. Almost right, right? So the end of this tube, right, is what is sensitive to those temperature changes. So we can use a bigger bulb to record uh, these minute sensitive temperatures. So to increase sensitivity, we may use a bigger bulb. Bulb is just this end of the mercury of this tube, sorry, this thermometer, right? And the another term which is also used is range when we want to specify a type of thermometer. So this range is very simply the difference between the maximum and the minimum temperatures, right? So the maximum temperature on our thermometer, as we defined, it was 100 degrees and minimum was zero. So the range of this thermometer was from 0 to 100, as in 100 degrees. So it can record from 0, 1, 2, 3, 4 up to 100. So the range is defined as the difference between maximum temperature minus minimum temperature. So this is how we define a range of a thermometer, right? Okay, and so that's more or less it about some of these thermometers. There's one more thermometer that we can talk about. It is called the thermocouple thermometer, right? And so just give me 1 second. So let's quickly talk about this thermocouple. Okay, so thermocouple is a thermometer, right? And it's an electrical thermometer which uses the principles of electricity to measure the changes in temperatures, right? So what we do is we have two wires, right? Two different metal wires. Uh, and so I'll quickly draw this thing. The schematic looks like this. So this is one wire. It is connected to a potential difference measuring device, a voltmeter. This device measures the potential difference between the two ends, right? So, for example, we can pick this wire to be a copper wire, right? This is one wire. And the other wire is any other metal, and it's something like this. So actually I should give it some other color. Let's give it some lighter color. Let me see, yellow. All right, so now you can see there are 2 points, right? This one and this one. Now these points are called junctions. So this is junction 1 and this is junction 2. So what happens is when these two junctions are at different temperatures, then you will get a reading in this voltmeter, right? Which means that whenever there is a change in temperatures, you will get a reading in this voltmeter. That is to say that the temperature difference between these two junctions between 1 and 2 will produce a little amount of voltage, a small amount of voltage, which would be recorded in the potential difference measuring device. Now, this voltage is essentially uh, directly related to current, right? So the bigger this voltage is, the bigger the current flow is, right? So you can, I don't know if you have seen that cartoon where you have someone trying to crawl through a rope. He's trying to go in this direction, and there is someone pushing this person to go in that direction, but there is some rope that is trying to squeeze him so that he does not go in that direction. This rope is like a resistance. So it's resisting this motion that it's going in this direction. The person that's pushing it is essentially the voltage. And this thing that is trying to go is, you can say it's a charge, for example. And if it moves, then it produces current, right? So it's essentially current. Charges are essentially currents. If they're moving, then they produce or give rise to currents. So you can think of these voltage, resistance, and charges in this way, at least for now, right? Until we talk about electricity and magnetism. So these small amount of voltages will produce small amounts of currents. Now imagine if the temperature difference between these 2 points, so suppose there will be T1, this would be temperature T2. If T1 and T2 are the difference between these two is very large, then it would produce a very big amount of current. And now you might say, why do we use a thermocouple? We can use a liquid and glass thermometer as well. So these different types of thermometers are used for various different kinds of purposes. One thermometer may be suitable for one purpose, while the other one is suitable for some other purpose. And one of the purposes for a thermocouple is that it is used where the temperatures change very quickly, right? So it is used when changes in temperature are very rapid, because now this is able to give you, this will, as soon as the temperature changes, you will get a response to that. That would be this potential difference. You will get a number, a value. So it's like temperature change, you'll get a response, you will know that the temperature has changed, right? It might beat or something. While if you're using liquid and glass thermometers, it's very hard to keep the track of temperature if it's changing very rapidly, because in liquid and glass thermometer, if you remember, the task was that this mercury should become stable. And when it becomes stable, you give it some time to become stable, and then you measure the temperature. Remember, right? So in thermocouple, if we have these rapid changes in temperatures where there is no time for this mercury to become stable, right? We use thermocouple, and we get, in response to the change in temperature, we'll get some potential difference. So it would be like a beep, 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 beep. You'll get the sound when the temperatures are changing. So you can easily tell that there are temperature
Teacher,
changes which are being recorded.
there are also electric thermometers.
You're talking about specifically thermocouple? It is an electrical thermometer. Yeah.
Is it inside of the thermometer in our houses?
You can say that this thing with which you changes change the temperature. I don't know what is that device specifically called, but it's a device on which you turn this dial to change temperatures, right? So it changes the temperature of the entire room. So you can say that it's used in those as well, right? Okay, so any question from this thing?
No, I have no question. I understand this.
Okay, all right, perfect. Anyone else having any other questions?
In the question we did earlier, so
Sorry,
can you
yes,
hear me?
Irma,
Can you hear me?
can you repeat what were you saying? I cannot hear you.
Can you hear me now?
I
Hello, can you
cannot
hear
hear
me?
you, Irma. Uh, your voice is very low. Can you instead type in chat so that I can
Okay.
immediately? I think that Irma was referring to the example that we did. Irma, you typing in chat? I was asking the question we did earlier, are these values present in the question or we have to figure them out? Okay, all right. So I'll tell you which values are given, right? So these two values that I'll quickly highlight, these are the ones that would be given to you, right? And this value L theta is the one that you will look at the temperature thermometer. For example, it might be given to you, or the question might say the length of the mercury tube at that specific temperature is this value, right? Your two accounts with the same names. Oh, okay. So this value can be read off this thermometer, right? Or in the question, it might say that the temperature that we want to find out at that, the length of the mercury thread is this, right? So in this case, it's 14 centimeters, right? So maybe they'll say, what is the temperature when L theta or the length of the mercury tube is 14 centimeters? So that's how you will know that they're talking about this L theta, right? Is that clear?
Yes, it's
Okay, all right. Okay, so move on to the next topic quickly. Now let's see how temperature, pressure, and volume uh, form a relation, right? So temperature, pressure, and volume. So we are familiar with temperature now. We have talked we have talked quite a lot about temperatures, and we have seen pressures as well, right? In the last topic that we were doing on pressures, we talked about pressure in liquids, in gases as well, right? And on solid surfaces, which was simply F by A, force per unit area. Right? And we have very good knowledge about volumes as well from our discussion on. Well, we talk about volume in every chapter, but we specifically talked about it in mass, weight, density, and volume, and that topic. So now let's see how these three variables or quantities are related to each other. So to understand that, we'll first have to look at something which is called the Brownian motion, right? So Brownian. Now it's actually very interesting because this idea was about the movement of particles, the random movement of particles. That even though they're not living things, they are continuously randomly moving, right? And this motion was discovered by Robert Brown, hence it's called Brownian motion, right? And it has to do with the random motion of particles, even though these particles are not living. So initially, before this person figured this out, before Robert Brown figured that random motion of particles exists, that even if these particles are non-living things, they are continuously randomly moving. People had observed this effect before as well. But at that time, the only problem was they did not know that they thought that this motion is specifically uh, reserved for living things. So because they never saw these particles, non-living particles moving randomly, they always came across with this thing that we have pollen grains, for example. Sorry, not pollen grains. Uh, yeah, it was pollen grains, if I remember correctly. Pollen grains, they thought that it is the living nature of these pollen grains, that these particles in this pollen grains are randomly moving because they're alive. But Robert Brown took some other materials. He took different materials, maybe if I remember correctly, I think it was a stone that is grounded completely, right? And very finely grounded stone. And he placed that under a microscope and he observed those particles. And he saw that these particles are also randomly moving. So I don't know if I can, I'm going to try to draw. So this is a slit. On this slit, he placed these freshly, not freshly ground, but finely ground stone particles, and he observed it with the microscope. So he's observing it from here. And for the experiment to be clear, there is a source of light over here so that you can observe it, observe them clearly. What he saw was that when he observed it with the microscope, he saw that these particles are randomly moving. So we have these particles. That's what he saw, and he saw that these particles are randomly moving in various. It's also called the zigzag directions, right? So this was the instantaneous random movement of these particles, and he recorded the path of these particles by picking one particle and then seeing how does that particle moves. So he saw that this particle, for example, if I pick this particle, he recorded the path by drawing lines. He traced the path of this particle and he saw that it's something like this, right? So this is where we got the name zigzag direction. So he saw that this is the path of the particles, and it was a random zigzag particle was followed by the particle over a period of time, right? And this was observable through the microscope as tiny specks of light, right? And these specks of lights are caused by, because of course you have light over there, right? And when the light particles collide with these tiny particles of stones, uh, they will be scattered by these particles. The light will be scattered, and that light will be seen as bright specks of light, right? So this Brownian motion is then the molecules moving randomly. You can say molecules or atoms uh, moving randomly. And why do they move random? They move randomly because they are going to collide with other gas molecules or light particles, right? So because of collisions, right? Uh, with same particles or light. So that's why they're moving randomly. So, is there any question, anything that is not clear about Brownian motion, about this random movement of particles?
Is this similar to the kinetic particle theory?
Exactly, right? So the kinetic theory. Uh, can you say it again? I don't remember the name. It's the kinetic model of matter, right? Kinetic theory of molecules.
Yes, yes.
That's what you're referring to. Yeah, exactly. Right. So okay, it's the kinetic model of matter, right? And it explains and predicts the macroscopic properties of different materials, right? The kinetic model of matter. So, for example, things like why densities of solids are greater than the density of liquids, and then those are greater. And those are greater than the density of gases, which we have talked about as well in the previous lectures, giving this examples that these are solid molecules, atoms, and they're very closely packed with each other, right? And this is what we are coming on to now. So clearly you can see if I pick a region of volume, suppose I'm picking this region of volume. In this region, I can see that there are more number of atoms packed in this volume. If I compare this with liquid molecules, which are slightly loosely packed, right? And if I draw the same region of volume for this case, I can clearly see that in the same region of volume, I have less number of particles or atoms uh, placed in this volume. And that means that that explains why a solid is more denser usually compared to liquids. And then you could go on to the example of a gas where the molecules are even further apart, and that explains the lowest density of gas molecules, or gas particles, right? So that's Brownian motion. And now let's also talk about temperatures, right? And how temperatures are related to the kinetic energy of particles. We have talked about this slightly before as well. Temperature and kinetic energy. So you're familiar with this thing that if you have particles, we saw initially that the if the temperature is high, that means that something is hot. It only means that these particles are moving with very high velocities. And if the temperature is small, less, that something is cold, then coldness is just particles moving with very slow velocities.
Less than
So
1 minute.
this relation of less than 1 minute, all right. So I just finished it with this, that the temperature in this way is directly proportional to the velocities of these particles. In fact, it turns out it is proportional to the square of the velocities of the particles. We'll not go into the very deep mathematics of this thing, but you see that this means that temperature is essentially proportional to the kinetic energy of these particles. Kinetic energy is half mv squared, right? So that means the higher the velocities of these particles, that means that higher the kinetic energy, and that means that higher the temperature. So temperature is nothing